This video is intended to introduce you to the side-angle side similarity theorem and teach you how to use it in proofs. Let's first take a look at what this theorem says. It says if you have one angle in one triangle congruent to a second angle in another triangle, and the lengths of the sides that include these angles are in proportion, then the two triangles are similar. So let's take a look at what this might look like in a picture. So I'm going to go ahead and draw my two triangles. And it says if you have one angle of one triangle congruent to one angle of a second triangle. So let's just suppose these two are our two congruent angles. And the lengths of the sides that include these angles are in proportion. So maybe the ratio between those two yellow sides is exactly the same as the ratio between those two green sides. That would make our pairs of sides proportional. Then we could go ahead and conclude that those two triangles are similar to each other. All right, so let's go look and see how we might use this in a proof. First thing I'm going to do is, of course, label the information that they give to us in the problem. And then I'm going to take a look at what it is they want us to prove. Now this proof isn't quite so straightforward because they don't come right out and say that they want us to prove that these two triangles are similar. But if I look at what they do want us to prove, they want us to prove a pair of angles that are congruent. The angles that they want us to show, or they want us to show congruent, are VWZ, which is that yellow guy right in there, and XYZ, which is that yellow guy right in there. So I have some strategies I could use for doing this. If I could show that those two lines, VW and XY, were parallel, then that would force the corresponding angles to be congruent. But unfortunately, I really don't have a way to get those lines parallel. If I could prove that a pair of triangles that contain those angles were congruent to each other, then I could say the angles were congruent, but I really don't have a way to prove the big triangle and the small triangle congruent. That would be kind of silly. Or lastly, if I could prove a pair of triangles that contains those angles to be similar, then I would have those angles being congruent to each other. So kind of the method to the madness here is going to be to prove that the blue triangle is similar to the green triangle, and then because those two yellow angles are corresponding angles, they would have to be congruent to each other. So that said, we're probably going to use those blue side measurements to establish the fact that the lengths of the sides are proportional. Hopefully, as you're looking at this diagram, you're seeing that red angle at the top of the picture that's common to both triangles, so it has to be the same in both by the reflexive property. And that's the gist or the direction that this proof is going to take. So I'm going to go ahead and start out maybe talking about how angle Z is congruent to itself by the reflexive property. I need to establish the fact that the lengths of those sides that surround angle Z are in proportion. And to do that, I'm going to go ahead and write some ratios. So I'm going to go ahead and compare the length of XZ to the length of VZ. And I can write a ratio for anything I want to. A ratio, remember, is just a comparison between two numbers. So the ratio of XZ to VZ is going to be equal to 12 to 4, which is really the same thing as 3 to 1 when I simplify. And the ratio of ZW or ZY to ZW is 6 to 2, which is really the same thing as 3 to 1 when I simplify. So I substituted in numbers for side lengths. That's simple substitution. Because these side lengths here have equal ratios, they're both 3 to 1, then what that means is that they're proportional. So I can go ahead now and write my proportion that says that the ratio between xz and vz is the same as the ratio between zy and zw. And I'm just going to say the same ratio makes the sides proportional. So here I've got my proportional sides. Here I've got my pair of included angles. I'm going to pull those two steps together and go ahead and conclude that the two triangles are similar to each other. So triangle VZW, the little blue one, is similar to, and I have to be careful when I name my second triangle. This angle in the green triangle that corresponds with V is X, Z corresponds with itself, and angle Y will correspond to angle W in the blue triangle. And that is side angle side similarity. And once I've established the fact that those two triangles are similar, I know two things. I know, first of all, that the lengths of their corresponding sides are in proportion. Secondly, and more importantly for this proof, I know that the corresponding angles are congruent. I'm simply going to state when two triangles are similar. Corresponding angles are congruent. Awesome. All right, let's go flip up to the top of the next page and we'll write the second proof. I'll give you a minute to go ahead and take a look at this one and mark your diagram. All right, so this is looking a little tricky. When I first start to look at these side lengths here in the proof, I'm thinking to myself, use similar triangles. If I could establish the fact that those side lengths are in proportion, then I could cross multiply and their cross products would be equal. So that's kind of what I'm thinking of, or the direction that I'm thinking about going. So DB is that segment right there. EC, the next piece, is that part right there. FC is that purple segment right there. And then lastly, BE is that part right there. So the two triangles that I'm aiming to prove similar to each other are that small red one and the slightly larger purple guy. And in looking at the picture, I have no pairs of angles, I have no pairs of sides that are in proportion. But if I think about this big triangle ABC, this big triangle ABC is a triangle where two of the sides are congruent to each other. And because two of the sides are congruent, that triangle is isosceles, it's going to force the base angles to be congruent as well. So the angles opposite those sides are going to be congruent to each other. That's going to make angle DBE congruent to angle FCE. So that gives me one pair of congruent angles. And then looking at my picture, I'm seeing this piece here that's common to both of those angles that were congruent. If I were to subtract that piece away from both angles, what I would be left with is I'd be left with these pieces in here that are congruent to each other. So that would give me a second pair of angles. So this is actually an angle similarity proof. We're going to get to use some angle subtraction, which we don't get to use very often. We're going to get to use that theorem about an isosceles triangle. All right, so let's go ahead and get down to business and get her done. So AB is congruent to AC. We know that's a true statement because it's given to us to be a true statement. And because those two sides of the triangle are congruent, we know the angles opposite are congruent. So that's going to make angle DBE congruent to angle ACE. I'm going to be very careful to talk about a triangle here. So when two sides of a triangle are congruent, the angles opposite those sides are congruent. So there's my first pair of angles. Now I've got to establish the second pair of angles congruent to each other. I'm going to go ahead and start out with these guys that were given to us. So angle DEC is congruent to FEB. We know that's a true statement because it's given to us to be a true statement. This piece that's common to both, the yellow piece in my diagram above, I know that's congruent to itself by the reflexive property. We haven't looked at an example of one of these in a while. This is a nice one to look at. So now if I go do a little bit of angle subtraction, I'm going to be very careful to start with the larger angle. So the larger angle is angle DEC, and if I subtract out angle DEF, remember that as I do my subtraction, I'm going to subtract left sides from left sides and right sides from right sides. So that's going to be congruent to what I get when I subtract angle FEB minus angle DEF. And I've subtracted equals from equals. That's the subtraction property, or if you prefer, the subtraction postulate. Taking a look at my picture now, if I go ahead and start with angle DEC, and I subtract out this yellow piece in here, what I'm left with is this little blue guy in here, angle FEC. And likewise, if I do the subtraction on the right-hand side, angle FEB minus angle DEF, that's going to give me angle DEB. And that's just substitution. So pulling these pairs of angles together, we've got a pair of triangles that are similar. So our triangles are triangle DBE and the second triangle FCE. That's the angle-angle similarity theorem. Once those triangles are congruent, I know that their corresponding angles are congruent, and I know that their corresponding sides are in proportion. What I'm concerned about here is I'm concerned about these pairs of sides. So I know that the ratio between DB and DE the same as the ratio between the corresponding pairs of sides in the purple triangle, FC and EC. And that's because when you have two triangles that are similar, the lengths of their corresponding sides are in proportion. Lastly, to wrap this up, I'm simply going to cross multiply. So dB times EC, the product going in one direction is going to be exactly the same as the product going in the other direction. I'm going to say cross multiplication. If you want to get fancy, you can say the product of the means is equal to the product of the extremes. Awesome. At this point, if you have any questions, feel free to jot them down, or better still, shoot me an email. The next time you come back to class, we'll use our class time to practice writing some of these proofs. Till then, see ya.